people that are here already don't need to wait longer. What do you think? Okay then, so welcome everyone. My name is Erik Billing, and I will say a few words about my research. I'm a researcher at the University of Skövde in Sweden, and I work with robots all day long. So we will make a quick detour in sort of the future of robotics and what we can expect to see in the near future. So we start with this little video. And if you have any questions during the seminar, please just write in the field or say something.
Hello, my name is Nixie, and I'm an MDS robot. MDS stands for Mobile, Dexterous, Social. Mobile because I can move around. Dexterous because I can use my hands to touch things or even pick them up. And social because I can communicate in many of the ways that people do. I can tell you that I'm sad, mad, confused, excited, or even bored just by moving my face. But I hope you can see that I'm very happy to have met you. Thank you for visiting me, and I hope to see you again soon.
Okay, I know that I'm in Sweden, right, and I know that many of you are at the other side of the world, and that Sweden have sort of a reputation for being just cold and ugly. But I just wanted to start by saying that we have 25 degrees outside today, shiny weather, and almost sun all day around. So it's not horrible all times of the year. I will, however, not speak that much about the weather, but rather about the future of robotics and what we can expect to see. So I will start a little bit by going into what a robot actually is, and maybe a little bit of what it isn't, and then basically dive from there into into different kinds of applications that we see, and that I also partly work with. So this is one robot that is called Now. It's produced by a French company called Aldebaran, and it's basically a research platform, one of the robots that I work with personally a lot. As you can see, I mean, it looks like we expect the robot to be, but that is of course not the case for all robots. I mean, this is, in my opinion, just as much a robot as the Now. It's a standard lawnmower that we, at least in Sweden, see now on soon every second garden I pass on my walk to the office. And to be honest, that's more or less what we have got so far from robotics research in terms of everyday applications that really work in our daily lives for private industry. Of course, we've got a lot of applications for closed industry, factory floors, and that kind of things. But this one, and of course similar things for vacuum cleaning and so on, I mean, that's what people associate today with a robot, which is, I mean, to some extent a bit sad, thinking of all the work and research that's gone into this field over the last 30 or 40 years. However, in terms of research today, I see two major trends, and this is one of them, saying basically that we are investigating how to build robots that can work in an everyday environment with people, cooperate. I mean, where we are not working on a factory floor, basically, where we should be able to bring a robot out on the street or have it in our homes, and it should basically function well without being perfectly adjusted for the robot. But there is also another side of robotics research, and that is this, that we can basically ask the question, what can we learn about ourselves, about how the brain works, or how human cognition works from building models. And those models take place not only as abstract things in a computer or on paper, but also in forms of robots. And there are strong arguments why we want to really build these models into machines to see that they actually work. You can build a machine just like you were thinking that it would work inside the brain. Of course, there are many important differences between how the brain works and how the computer works, but that doesn't depend. That doesn't hinder us from building models that resemble some aspect of how the brain works, and that is a large part of what I'm doing myself. Okay, so further on to the kind of applications that we already see today that are present out in this, and here's one of them. So this one is called Ream. It's from PAL Robotics, and you can basically buy one of these robots. So it's a product. It's not just a single thing built on a lab somewhere. And it's intended for being used on, in gallerias and the kind of environments you see here in displays of different kinds, where basically you can have this robot showing the way to a certain place, like a certain store in a shopping mall or something like that. And it can work in a real everyday environment with humans, at least given the fact that the floor is flat and so on. And it can do obstacle avoidance, so if a person walks in front of it, it can avoid it. And you can, of course, you can speak to it, you can use it for Skyping and communicate using the screen mostly to say where you want to go or what kind of information you're searching. So that's not revolutionary in any way, but it's a concrete example of the kind of applications I think that we can expect to see more in the near future. Okay, here we go to probably the most famous robot in the world, and I guess some of you already know. Okay, so this one is built by Honda, called Asimo, and just like the Now, this is really pictures our idea of a robot, and in the research field we call these robots humanoids because they are designed for beings like humans in many ways. There are arguments for building robots like this. One thing is to say that our everyday environment are suggested for people. So if we want a machine that can really, interact with people in an everyday environment, get around, walk the stairs, take an elevator, everything, it needs to be of a similar size and a similar shape as a human. And that is basically pictured here by Honda, is showing that that's at least technically possible. Asimo is often referred to as a single robot, but it's actually a whole series of robots built over the last 30 or 40 years, and they have new versions coming out now and then. I think this is the 2011 version that we see here. And at this stage, it was a big thing that it can it can walk stairs, and it can run. At least technically, it can run, meaning that it actually lifts from the floor with both feet for a short time. And I mean, it can shake hands, it can kick a football, it can do numerous everyday things. Still, it's not very clear what you actually should use it for in any way. Honda has put loads and loads of money into this machine, and is arguing at least that they get it back in terms of marketing money. I mean, this robot has a whole fan club of people going around and I mean, attending the different displays where they show the robot and yeah, I mean, demonstrate the new features and so on. So this is really the first robot that sort of reached I mean, a real superstar kind of position, and it certainly has. Here is another example.
From Intelligent System Corporation. Pyro, modeled on a baby harp seal, displays emotional responses to external stimuli, which are input via a range of tactile, light, audio, and temperature sensors.
Okay, so this category of robots, where Pyro is probably the most debated one, is a big growing field within the world of robotics at the moment. There are several, I mean, investigations that have, I mean, argues at least that these robots are, I mean, they can successfully use to help people, for example, elderly people that are alone and need company of some kind, or people with different psychological diseases like depression, for example, and they are, I mean, explicitly designed to make people feel better. Still, I would say it's too early to say what is really gained with this kind of robot compared to I mean, a pet or just a normal teddy bear. But nevertheless, I mean, this is something that many. I mean, this is clearly something that we can do with the robotics, and we add something in relation to a traditional teddy bear, even though you might ask what the value actually is. And also on top of that, it might be situations where you for one reason or another shouldn't give an animal, I mean, a real pet to a person for, I mean, for example, that the person can't really take care of that, even though it needs, the person itself needs company. So I think this is a bit, I mean, difficult and also partly sad development of robotics, but nevertheless it's a big thing that we will follow and also see the ethical consequences of. I mean, really, what's the idea of humans being associated with the robot or a machine rather than people or animal. Okay, so now to something quite different.
How are you? It was just great. What's this? I love driving. There we go. Way to go.
Okay, I'm sure that many of you recognizes this one. It's the Google car. In Sweden, we also debate a lot regarding the Volvo cars. I'm actually in town, in the one town where the largest Volvo factory is located, and they have a similar program of providing driverless cars. They are usually careful not to say autonomous cars because, of course, the driver should still be in control, but you are doing that control by saying where you're going, not exactly, I mean, not holding the wheel, basically. I know that Volvo at least announced that they are aiming for releasing cars like these on the market at 2020. So that is, I mean, only 6 years ahead from now, right? And I'm myself expecting this to be the really next big thing, that in terms of a technological change that we as everyday person might experience, maybe similar to I mean, the introduction of smartphones or the personal computer. And I mean, that will also change how people are able to commute, for example, or in different ways affect our lives. So, I mean, this is maybe doesn't look like a robot, but in every, I mean, in many technological aspects, it's the same kind of research and the same kind of technology under the hood as you find in the Honda's Asimo or in this little cute Now robot that I'm working with myself. Okay, here to something quite different. Okay, this one is called the White Cat. It's developed by Boston Dynamics that recently was bought by Google. So as a first glance, I mean, it might seem weird that Google buys a company developing walking robots, but when you see the connection to the Google car, where clearly, I mean, the Google's map technology is one thing, and then Google Street View above anything is one thing that makes that possible. It's also clear that this kind of technology might go in sort of to the other end and help creating robots that can not only navigate on roads, but maybe also on many other places. Many might think it's being a scary future of a machine like this running over in 70 kilometers an hour. But we will see where this takes us. In any case, I mean, it's a technology development that happens either you like it or not, and we will see what it's used for in the end. Still, I would say that that's quite open, as many of these things are. Also, I want to say to the organizer of the meeting, Damaris, that I am not sure I see any feedback or questions from the from the people. So if you maybe could help out with that, I just see a list of you and me, so the staff names. So in case there are questions, I'm not sure that I see them, and I'd be happy to take them. So just so you know. Okay. One more little thing before we continue. This is the first video in the scene that is not completely true. I mean, it's true in the sense that this has, of course, been done, but it's a remote control. It's not autonomous. And you, of course, also you see that it's speeded up quite literally. And I think this demonstrates another interesting aspect of where we are in robotics research at the moment. I mean, we have robots that dexterity-wise can do what we want them to do. That is, for example, being a service robot in our homes and cleaning up from our kids and so on. But in terms of the robot control, we are not there yet. In that control, there are, of course, many problems, like the perception of where objects are, what kind of grasp that would be best, how to plan the whole procedure, what is the task about, where, I mean, what is actually the goal here, and so on. And in that sense, I would say that we are much further away than in the sense of creating a machine that I mean, in terms of its dexterity, can achieve these things. Also, another aspect is the price tag. What you saw here was a previous version. That was a PR1 robot from Willow Garage. And there is, I mean, the most famous one now is PR2. It goes for 280,000. And that is, I mean, even if the controller would work, that is a bit too much, right, for the average, I mean, house cleaner machine. However, there are many things happening at the moment in this regard. Unbounded Robotics just now during the spring released this UBR1 robot that goes for only 35, and okay, it only has a single arm, but in most other respects it's quite comparable to the Willow Garage version, and the Willow Garage has for a long time been really the top-notch of I mean, a classical indoor kind of service robot. We also have the Now robot that I showed earlier. Up to recently, it went for 16,000, but now, due to more competition and a different production procedure, they were able to more or less half the price, down to 8,000. So you're seeing that, I mean, these products, even though they are still expensive, they are approaching a limit where they are actually available to consumer products. So since the Now robot is one of the things that I have been working most with, I was thinking to go into a little bit more detail of what this robot is and how it can, what it can do basically. So technically speaking, this has two computers in it, one located in the chest and one in the head. The main computer is, the head computer is just, I mean, running a Linux distribution, so it's not, I mean, in any very strange kind of, it's a normal, communicates over a standard wireless, and you can request sensor data and send motor commands to it. It has two cameras, both located in the head, one, I mean, in the top row here, and one at the bottom in the mouth, more or less. So not in the eyes, surprisingly. The eyes are instead used to just display different colors, which is nice for social communication. You can give some feedback to the person interacting with it. It has touch sensors on the head and on the hands, and also bump sensors on the toes, on the feet. So so it can to some extent sense when people touch it, and also when it walks into things and so on. And of course, you can control the joints nicely. So in that regard, you can, I mean, it can do quite a few things. It has a few ultrasonic sensors, that is sound-based sensors in the chest that emits pulses of sound that goes back, and you can measure distance in that way also. So I mentioned earlier that it might be a bit difficult to really find the use for these kind of robots, but here I think is a very good example, and also a project that I'm working with myself at the moment.
The most amazing thing about these guys, made by French company Aldebaran, is how they have captured the imaginations.
Get me one to play again.
Of the autistic children like Khalid, Stephen, and Daniel at this British school.
Touch my right hand. Congratulations.
With the teacher's guidance, the robots teach them to focus, converse, imitate, and even pick up on the subtleties of human emotion that these kids struggle to identify.
Let me give you a clue. It may be joy, surprise.
Okay, so what you're seeing here is basically I mean, autistic children interacting with this robot, and they do that quite nicely. And we should remember that many autistic kids have severe problem of doing things like imitation or any kind of social interaction with other people and other kids. So the goal of this, what we see here is basically that a robot like the Now appears to be very well suited for interaction with kids. They like it basically. And one, I mean, honestly, we don't really know why this is so yet, but one theory is that the robot is simpler. So we know that autistic children get overloaded by social signals in many respects. They basically have difficulties to select what kind of features of facial expressions, for example, or gestures that are relevant for the social interaction. And another and a consequence of that is that these kids often get a very strange response from other children and also from grown-ups, since their social interaction doesn't really work. And the advantage of the robots here is that it's simpler. It's a robot. It moves a bit stiff like this and so on, and then it's easier for the kids to sort out. Okay, this is actually the important change here, because there wasn't that much else happening. Another way to think of that is to say that we can design the robot and more precisely say what should be the response to a certain action, and in that way make it easier for the kid to enter into a working social interaction where the kid doesn't feel that it is receiving strange or negative response. So in a new European project, this is a big project that will go 4 years and involve in many countries in Europe, and is coordinated by us here in Skövde. What we saw here on the video was what we call a Wizard of Oz setup. So you have the robot, you have the kids, and then you have a therapist, but you also have a third person sort of behind the scene remote controlling the robot, so it looks like the robot is reacting to the kids' responses. But what we want to do is to go one or a few steps further and really say, okay, so what can we how can we do it so that the robot actually responds to the signals of the kid without the need for this wizard sitting behind the scenes pulling the threads of the robot, so to speak. What we'll do in practice is to implement techniques for to recognize what the child is doing, and then also based on that decide what kind of response the robot should be. So in that, among other things, there are the issue of identifying where the child is looking. Is it paying attention to the task or to something completely different? Has it achieved a given task? Has it not? And so on. And then, of course, also based on that, we want the robot to be able to give some reward or ask the child to try again, and so on. So basically, what we are doing is to take a scenario that, like an imitation game with involving toys, that the therapists are already using today when training children to recognize social signals, like doing imitation, for example, and take that scenario, and rather than having the therapist, having the child imitating the therapist, we will have the child imitating the robot. And along with what I explained earlier, the idea of this is, of course, that this should be easier for the child than what actually is possible to do with the therapist. This is not about removing the therapist or just having the child playing with the robot, but the idea is rather that the robot should be a tool that the therapist can use in everyday. On some sessions, of course, not um, another aspect is also to collect data. I mean, all the sensors used, I mean, available on the robot will, I mean, can be used for collecting data in a different way than is possible otherwise, and that might be beneficial also for I mean, developing therapy that doesn't involve a robot at all, just using this as a diagnostic tool, basically, to see how we can come up with new type of scenarios or new type of exercises that therapists can use. So, I mean, in this, there is also a big ethical question, of course, because we should remember that I mean, as soon as we bring in technology like this into the rooms, like among other things, collecting data, there is also a request to use that data in different ways that is not entirely obvious that that's the right thing to do. I mean, we have already received signals that it might be, I mean, the parents, for example, want to have access to that data, and at the same time, the child is choosing to speak and open itself to the robot rather than opening itself to the parents. And to what extent should you actually allow the parents to use that kind of information that we can get through that interaction? That's not obvious at all what is the right decision there. So therefore, in this project, we also have a whole work group focusing on ethical questions and seeing, I mean, what are the problems of, just as in the case with this robot seal, what are the problems of having people or I mean, in this case, kids, I mean, attaching themselves strongly to a machine. Okay, so that for the application. Since this is within the framework of IT architects, I also wanted to give a bit more of a hardware or rather the how you build the software structure for these kind of applications. And I think that this 4-layer architecture is a simple and quick overview of how we build these kind of applications. So at the bottom you have the hardware, like this Now robot or a standard PC, and usually you have both. You typically have a few laptops, quite standard ones, and then these interact over wireless with the robot. And then, as I mentioned before, the Now robot is running a Linux distribution, and on the laptops we are also running a common operating system, so nothing really special there. What's a bit different is this middleware that we have. There are many of those. Robot Operating System, or ROS, is probably the most famous one. And there is also YARP, NowQI, and many others. And this software allows components to be moved in between hardware independently of exactly where they are located. And the integration is done using message passing. And these middlewares resolve problems like concurrency and basically if you need to offload one computer and have those components of the software running somewhere else, you can do that without reprogramming too much of the whole architecture. And on top of the middleware, you're running the particular application. So that would be, I mean, the precise programming controlling how to recognize attention of the kid or what kind of a response we should give in a different, I mean, in a certain situation. And here is a more detailed view. So typically we I mean, of course the operating system is used here, but we want to emphasize that this can be located on different computers. So we might have one computer resolving the real-time interactions with, I mean, for doing certain motions, and another one taking care of the more heavy camera or laser scanner data and processing that and so on. Okay, so another view of this abstraction is can be drawn like this. I would say that in terms of engineering or software development over the last, I would say, 50 years, we have focused a lot on I mean, hardware abstraction of different kinds. So we went from assembler to C, C++, and now we do a lot of stuff in JavaScript. And that's the vertical dimension I'm trying to illustrate here in this figure. So we try to describe behavior in a way that is less and less specific of the particular software or particular hardware that we are using. In robotics, we have a slightly different case going along the horizontal dimension in this figure, and that is moving from a predefined behavior to a less predefined or allowing machines to learn. And the reason we need that in robotics is that it's very, very difficult for the programmer to know beforehand all the different situations that this machine can encounter. So in contrast to a traditional I mean, traditional computer program that you run on Windows or Mac or something like that, you typically make a list of, okay, we want these features to work, we want the user interface to look like this, and we're creating these and these algorithms under the hood to achieve that. But still, we are all the way, I mean, specifying behavior very clearly beforehand, and it's up to the engineers, the software developers, to implement that kind of behavior. But in this case, we need to do something slightly different and just say that, okay, here the robot should be able to learn a wide variety of things. That could be like I mean, if you have a service robot coming to your home, you want to be able to teach us that okay, this is my kitchen, but in this particular case, we are actually storing the cutlery in the box, which is not in the kitchen, but somewhere slightly different. And be careful for this high threshold here between these two rooms, because otherwise it will fall over. And you should not be confused by that mirror there, because yeah, that's just standing in a weird way. So be careful for that. And I mean, don't go into that room because you know my wife she doesn't like the robots very much or something. So it's very hard for the engineer to know beforehand exactly which aspect of the environment that will be relevant for the robot to be able to capture that important distinction that of the world actually that we will need in order to achieve the right behavior out in the physical world. And that is the way that's done today in our field can be seen along two partly opposing trends in the field of robotics. And one trend goes towards more classical engineering, that is often referred to as the deliberative or hybrid architectures. And there you basically define your behavior in high-level terms, and then you try to create algorithms that can connect that to the physical environment, so that if we know beforehand that there will be important to know where the cutlery is, we create algorithms to recognize forks and knives, and then we are fine. But there is an opposing trend arguing that that you can't really do it like this, but what you should do is allow for emergence of new behavior, and that one example of that is clearly biological systems like humans and animals. And in these systems, the embodied aspects are critical. These are often referred to as embodied or emergent robotics. And here we clearly can't or shouldn't do hardware abstraction anymore, but rather we should do behavior abstraction, if you put it like that. working very close to the sensors and actuators of the robot. Because if you want a certain behavior to emerge, you are very, very dependent on precisely what kind of sensors and actuators that machine has. So in that sense, it's almost like the wrong direction to try to abstract away from the hardware in the way that we are doing today in other types of engineering. So with that said, there is a very interesting trend. We will see how that goes in terms of robotics, in just engineering-wise, of what kind of divisions we will see in the future and how software is actually built. I would say that we can probably see quite dramatic changes there, which might affect also other types of programs, not only the ones running on our robots. Okay, so with that said, thank you very much for listening, and I'll be happy to take any questions that you have. So thank you very much.
All right, that was awesome, Erik. So we will see if there's any questions that anyone had. Fantastic presentation. Let's see. All right. Let's see. So.
And again, a note to the organizer here. I'm not sure that I'm seeing any questions written by the audience. So if there are any, please forward them to me or explain how I should get that up here in GoToMeeting.
Okay, so let's see. Well, if nobody has any questions, I actually had a question for you, Erik. Can you still hear me, Erik? All right. Oh, sorry. Let's see. Hold on. Can you?
Okay, then I think if you're all happy and there are no more questions, yeah, we can finish. Or what do you think, Damaris? Okay, yeah, I'm here. No hurry at all. So I got a question here. What publicly available frameworks, if any, are you using? And with the framework here, I assume the software framework, right? Several of those I mentioned. Let me go back to that slide. This robot operating system, or ROS, is an open source project. Anyone can just go and download it if you want to. And similar with YARP. YARP is a much thinner thing, so it's basically a message passing system for writing software that runs on many machines simultaneously. Now QI is developed by Aldebaran specifically for the Now robot and a few other robots they have. and it's not open source at the moment. I mean, myself, I'm using YARP and now QI, and in that sense, I mean, parts of our software that we write is completely open and free, and parts that based on proprietary things. So that it differs a bit from project to project, I would say, what we are using. Okay, I got a question here. What would you suggest for a young child who wants to enter the field of robotics? And yeah, that's a very good question. I will actually already next week have a couple of children coming visiting our lab and interacting with another robot, doing a small little game that we have where the robot is supposed to recognize a few wooden cubes. And that's one way, I guess. But in terms of programming the robot or learning how to think in that, I mean, I would say that the Lego Mindstorms is by far the best that we have. We actually used it in introductory classes for our new students, and the sad thing that these 19 or 20-year-old kids, they are actually not as good as the kids that come. They are 8 years old and they play intensively with Lego all the time, and they can create tremendously advanced programs just in Mindstorms. So I think there are many ways, and I mean, anything that yeah, opens up and creates curiosity for I mean, for the field will, I mean, learn to enjoy engineering, and a bit nerdiness maybe would be good. But otherwise, I guess I myself have a cognitive science background at university, so I have both a background in I mean, biology and on how humans and animals work in terms of how the brain functions, and a side which goes more towards software engineering and classical computing science. Okay, so what is the biggest thing holding robotics back? Battery, tech, software, hardware? Yeah, well, I mean, I would say that the batteries are getting there. They were a big problem, but the mobile phones, the smartphones, are helping out a lot in that respect. I would say that a little bit, like I was hinting with this little video here I had. Okay, so here we go, this one. I think this is a good example of I mean, price is one thing, but above anything, that's, I mean, perception and I mean, the ability for the robot to autonomously interact with the environment and recognize objects in a stable fashion. We can do that in a predefined session. We will know beforehand. Here's one of the wooden cubes I use for interacting with the robots, and it works perfectly as long as we have a robot, have a cube. But as long as when I bring this copy, it doesn't automatically know how to grasp that or how to do with that. And we at the moment, we have no good way to teach it. We can of course program it to recognize the cop also and interact with the cop. But then we are in the same situation for the next object that comes into play. And online on that direction, there's also the durability of the robot. So if you look at the child entering into our world and learning to interact with all the kinds of objects that we have, that child, I mean, does mistake over mistake over mistake, and it learns from that. And it, I mean, the human body is breaks sometimes, but then it heals and it's fine. But today we are not even close to a robot that can stand that much violence, if you put it like that, as a child can do over, let's say, the first 5 years of life. And I would say that in order to really allow a robot to go through that process and to learn everything it needs to do in order to interact in an everyday environment, we probably need about that much time. So that's another critical side of the coin, I would say. Okay, so Damaris mentioned that that was the last question. I'm very happy for the questions, and thank you again for listening. And I hope you have a calming day. Here is soon evening, so but we have a few hours sun more. So thank you very much for today.